that everyone is doing good. I hope that you have a nice weekend. And in this week's lectures, we are going to continue with our discussion regarding the interprocedural data flow analysis, but we're going to go beyond what we learned in our lecture last week, where we discussed just how we can, generally speaking, do interprocedural analysis that crosses method boundaries, and we're going to handle certain cases that we couldn't in the previous lecture. But before we do so, I just have a couple of things that I want to share with you. So I see that for assignment 0.0, almost everybody in class has chosen a partner for the assignment, which is basically the course project. If you haven't, please talk to me soon. Whether you have or you haven't, please let me know as soon as you can. I would like to discuss your project ideas with you as soon as you can. I don't want this to wait until the day before you do your project proposals, or worse, at your project proposal presentation itself. I would like that to get sorted out as early as possible. Just as a reminder, the proposal presentations are going to be October 20th, so that is exactly 2 weeks from today. So we still have a bit of time for discussing together what you might be up to for the course project, but I know you have many other courses, so start the discussion about your projects pretty soon. The second thing that I would like to talk about today is assignment 0.1, which is choosing your partners for the paper seminars. It is still due today by the end of the day, that is 5 p.m. Edmonton time. So please make sure that you choose a partner for your paper seminars. If you don't, it's going to be randomly assigned. As I mentioned in our very first lecture, the introductory or organizational lecture, those paper seminars are going to be spanning almost 3 weeks or 4 weeks, of our lectures, so the last month of lectures. And for those, there are 2 different student roles that you will be assigned, again at random, but you're welcome to switch papers in the same role if you don't like the paper you're assigned, as long as you agree with the other group that you're going to be switching with. And as long as you let me know beforehand, before the day of that paper, seminar, or presentation is due. Those are the couple of announcements or things that I wanted to discuss. Does anyone have any question about anything that is related to the course so far, or the assignments, or the project? Is everything clear so far? Can we choose the papers ourselves? You're going to be randomly assigned to papers, but like I said, if there is a paper that you really want to present in either roles as a presenter or a validator, you're welcome to reach out to the other group who's assigned to that paper and trade papers with them. I think this, throughout the years, I found this to be the most fair way to distribute or assign people to slots, so that no one takes a slot that is early on while others take slots that are late, so everyone has a fair shot at being assigned to slots as we go. But like I said, I'm fine with you switching papers together, as long as it's, like, if you're a presenter for, so let's actually go to the seminar schedule and look at the seminars there. So let's say you're looking at some papers on, I don't know, an UPSLA 20 paper, adding interactive visual syntax to textual code. Maybe you're assigned to that one, but you want to, I don't know, be a presenter for PLDI 20, fast graph simplification of interleaf reachability. So just reach out to those who are assigned as presenters for that paper, and you can switch or trade slots with them. You cannot trade slots with another role. It has to be the same role that you want to trade slots with, so that you get to do both presenter and validator for 2 different papers throughout the semester. So far, so good then? Any other questions or comments about the paper seminars or the projects or the assignments? All right. If you have any questions, just please reach out to me or Ifaz, and I'll be happy to answer your questions at any point. So, going back to our lecture, we previously in the last week we discussed interprocedural data flow analysis. We discussed inherited versus synthesized analysis information. Inherited information is information that is basically passed into the analysis, like information about the arguments information about the arguments and so on, like the input values. So I recall when we talked about this is similar to the VN in the monotone framework. Synthesized analysis information is basically what is the V out of the analysis in the sense of the monotone framework, and using the same terminology as the monotone framework. We've also talked about Kohler-Collier relationships and how we can make use of call graph information in our interprocedural data flow analysis. We've also talked about how we can differentiate between valid and invalid paths, and how we can use a call stack to help us out with that regard. And that led to our discussion about staircase of calls and returns, and how that enables us to ensure that every return that we encounter in our data flow graph or program supergraph, which is the interprocedural control flow graph, would have to correspond to a corresponding call edge, basically, along this graph. We talked briefly about demand-driven analyses and how that may need some different configuration for your analysis, specifically in the sense of having to propagate your information backwards from the point where you are requesting the information, like the statement that you're requesting the information at, propagating it backwards along the interprocedural control flow graph, and how that may affect the precision of your analysis, or even the soundness of your analysis, if you don't propagate backwards to all the potential call sites that may lead to calling that specific method that contains the current statement where the analysis is instantiated at or initiated at. We've also talked about various types of contexts, just to give you an idea, like object sensitivity, or using object as contexts, using call strings approach as context, using function approach as context, but just briefly talked about them. And today, in our lecture today, we're going to discuss those in a lot more detail, and when to use each one of them, what are the pros and cons of each one of them, and so on and so forth. Last thing we discussed in our lecture on Thursday last week was some important language features like threading and static initialization and so on, that will affect how you would compute data flow, interprocedural data flow analysis, or how you would model things in the interprocedural control flow graph. So if you recall from our lecture last week, the problem with context sensitivity was you have multiple call sites that are calling the same method. So let's say you have a method foo, and in method foo you're calling bar here maybe with 1, and you have a whole bunch of code here, and maybe you call bar again with 2, and maybe you assign this here, and then here you're going to say a plus v or something like that. And so you're calling bar for multiple contexts here, for multiple statements. You have multiple call sites to the same method, and you want your analysis to be able to distinguish between these two different call sites. And the reason you want that is you want to compute different information, data flow information at these two call sites. Specifically, here you have an argument that you're passing to the method bar, that is 1. Here you're passing to the method bar 2, and these potentially would compute different values from bar. And this is why we need context-sensitive analysis. So how do we actually conduct a context-sensitive analysis? There are multiple ways. So what do you think we can do there? I might have given away the answer by just advancing by mistake here in the slides, but entertain the thought. If you are an analysis engineer and you're tasked with finding an algorithm or finding a method or an approach that will allow your analysis to distinguish between different call sites in the program, how would you do it? Just remember the context when propagating the data facts. Okay, so you need to remember the context. And how would you do that? What do you mean by remember here? Make a tuple of the form data facts, call context. Okay, so you basically have a pair of, so instead of having your data fact as a single value, you want to have a pair of values. So every data fact has a label that says what is the calling context of it, right? Okay, that's pretty good. That's indeed one of the approaches that we're going to actually discuss in the class today. But do you think there are simpler approaches that you may use? So I will give you one hint here. So if you have taken any compilers course, or maybe some advanced programming language course, but specifically a compilers course, like in compilers, there is one optimization that compilers sometimes do that enable further optimizations, or there is one representation that compilers use that enable certain optimizations and make them easier to implement and easier to execute. So that is called SSA form, and this SSA form is single static assignment form. So single static assignment form. So what does that mean? That form basically means that we are going to give labels to variables in a program such that every variable, whenever you use it, is going to have an additional, you're going to increase the count of that label. So in other words, so if you are in method foo, and here you say v equals a, and then here you say b equals a plus c, and then here you see d equals a multiplied by 3, something of that sort. So that analysis will just scan the statements and then say, well, this is the first use of a, so I'm going to add 1. This is the second use of a, so I'm going to add 2. This is the third use of a, so I'm going to add 3. And so on and so forth. So we're going to do that for all the uses such that every single use is going to be unique for the same variable. Problems arise when you have an if condition. So if you have here if an if condition, and on one form you have a4 maybe here, and here you have a5, how are you going to join them again? And for that we introduce something called phi nodes. Phi nodes would be those functions that basically take a4 in this case and a5, and tell you what is going to be the value that is going to be used later on the next time an a would be used. So what are we actually doing here in this static single assignment form? We are kind of cloning the variable, so that every single time I'm using the variable, I'm basically using a unique instance of it, so that I can basically reason about def use chains or definition uses of that variable more reasonably, because I'm guaranteed that A1 is going to be used only once throughout my whole program, A2 is going to be used only once in my whole program, A3 is going to be used only once in my whole program. We kind of can do the same thing with methods as well. So assume here that instead of using variables, I'm actually calling bar with the value 1, and here I'm calling bar with the value 2, and here I'm calling bar with the value 3. So what if I can actually do the kind of the same thing here? I can just say this is going to be bar 1, bar 2, bar 3, and that way I am guaranteed that I'm only going to have a call to bar 1 only once in my program, a call to bar 2 only once in my program, a call to bar 3 only once again in my program. And that way I can maintain basically my context right away. I can just looking at the name of the method, I will know for sure where that method call originated from. I can identify uniquely where that method call is coming from. So more or less what I'm doing here is I'm doing method cloning. I'm cloning the method as many times as it is going to be actually called in the program, such that each use, in this case each call to that method, will be unique, would be easily distinguishable just by looking at the name of the call itself. So how can I do that? Let's have an example here. So here I have a Java-like program where I'm declaring an integer I with the value 0, then integer j is the value inc of I. I'm basically incrementing I by 1, and k is inc j. So what I'm going to do is the following. Assuming that this function here, inc, is this int inc x, and basically all what it does is that it increments 1 adds 1 to the parameter, then returns that again. So what I'm going to do is I'm going to have inc1, I'm going to have inc2, and I'm going to replace the first call to inc with a call to inc1, the second call to inc with a call to inc2. And it's doing exactly the same thing, right? But that's fine, that's okay. I basically just duplicated the code there. So how would that help? Well, first, before I say how that would help, it's obviously inefficient. I have too many copies of real programs. I mean, in the case of single static assignment, it was kind of okay to do that because I'm basically just adding a label to a variable. I'm not duplicating a whole bunch of statements in my program. Here I'm duplicating a whole method, and that method may be large enough that it is not going to be enough to fit my program, maybe I mean not on disk in a regular machine, but maybe on a device with limited resources like a mobile phone, for example, or a smartphone. So there are too many copies for real programs out there, and let alone if you have like a large SDK or a software development kit or a large library that other programs depend on. So it's inefficient. It's going to be an expensive operation because that means you have to go through every single use of a method in your program and then give a unique label to it, and then duplicate it as many times as that, add it to your code, replace all the labels. So you're still going to do some pre-processing before you can actually do your analysis. And what about recursion? Again, in the case of static single assignment in compiler optimization, that problem is not there because there are no recursion on variables, but in methods, a method can call itself. So there will be recursion there. So how are we going to handle that? Are we going to clone the method in itself? Are we going, and how many times are we going to do that? There has to be a limit where we have to stop at. But it's very simple, it's very easy to understand, and it has been done before with respect to variables, like I said in static single assignment, but there are many problems with it. It's inefficient, it's an expensive operation, and there is no obvious way to soundly and correctly handle recursion in the case of method cloning. So given all these problems, there is another method, a counterpart, to that method cloning approach, which is method aligning, doing exactly the opposite. Instead of duplicating the method, we are going to eliminate the method call altogether. And this is in fact, and again, like this is an idea borrowed from compiler optimizations, where compilers would replace a call site with the actual code of the method such that you can eliminate the overhead of creating a call stack, maintaining the call stack, pushing arguments on the stack and returning from the stack, and so on and so forth. And this can save actually significant amounts of time and improve the performance of your program. And this is one of the major optimizations that just-in-time compilers do at runtime to improve the performance of your running programs. So what does method aligning do? Again, like using the same example, what I'm going to do is I have the same method inc, and what I'm doing now is instead of duplicating the method, I'm going to eliminate the method call, take that code here, replace that method call with it, and see what happens to my program. So this is what's going to happen now. So now I'm going to have int x1 equals I, int y1 equal x1 plus 1, because that's the first method call, int j equals y1. That's basically my first method call. My second method call, when I increment it, I will have it as follows. Int x2 equals, and that should be 1 equals, let me fix that really quickly. There we go. Int x2 equals j, int y2 equals x2 plus 1, int k equals y2. So I basically, each three statements here replace an original call to inc. So what about this approach now? We lost procedural abstraction, which is the original thought behind having functions in your program. You can pretty much write your whole program in one big method that does everything. I mean, you're going to be limited by how many, like in a language like Java, you'll be limited by how many instructions you can fit in one method. But theoretically speaking, you can just write your whole program in one method. But you're going to lose the benefit of the abstraction that you have in separating things and separating concerns between different classes, different methods, different functions, and different functionalities in your program. There's going to be an exponential blow up. So every single use of the method, you're going to copy the method, put it in there. So your code size is going to explode that much. So again, the same kind of problem like duplicating code with method cloning, but here it might be even worse. And again, there is no obvious way to solve recursion here. Because if you have a recursive call, how many times are you going to inline the method into itself? There is just no obvious answer to that. But the benefit of that is we don't even need to do an inter-procedural analysis in this case. We can just do an intra-procedural analysis. Everything is going to be one big method. So no problem at all. We don't even need to worry about context in this case, because just context does not exist in this case. We have one big chunk of code, one big bag of statements that we can just go through like we did with the monotone framework and our intra-procedural analyses like from before, and that's just going to solve our problems. So we have two approaches, method cloning and method aligning. They have some benefits, some pros, some cons, but both of them suffer from the same kind of exponential blow up for code size, and they both cannot handle recursion. Do you have any questions so far about these two approaches? So there is a question here, how can we distinguish the method call in loop structure in method cloning? Okay, that's a very good question. So the question is about, okay, we talked about recursion, but what about loops? It's exactly the same. So loops and recursion in program analysis, they are very close in how they in the sense of the kind of problems they expose the analysis to, and the kind of solutions sometimes that we use to solve them. So it's the same thing. If you have a loop structure and you have a method call in there, again, the same question arises, like how many times you're going to inline that method in the loop. In compiler optimization, what happens in these cases is that you do something, you first perform something called loop unrolling. So you try to look for statements in the loop, or loop code motion as well. So first you try to look for statements in the loop that don't depend on the loop invariant or the loop induction. So you just remove them before the loop. And then you try to reason about how many iterations that loop is going to loop for. If you can know that at compile time statically, then you can just duplicate the code of the loop however many times you know it is going to run for, or unroll it however many times you think it may run for, so that you can sort of resolve that issue with method calls in loops. But again, I agree with you. It poses the same questions that we have with respect to recursion, whether it's looping structure, whether it's a recursive structure, or so on. You're welcome. Any other questions? All right. So what do? We have two approaches, both suffer from certain cons there, so we need to figure out something more systematic solution that we can use to solve this. So this is what context sensitivity actually provides, and we're going to discuss today two approaches that we may use that will help us eliminate some of those limitations of these naive kind of solutions to context sensitivity. So these two approaches are called call strings approach and the functional approach. What about the call strings approach? So in the call strings approach, it is kind of similar to what Jiaki mentioned a few minutes ago, that we are just going to associate the facts that we have with context strings. Pretty much like we did with the call stack in our interprocedural lecture last Thursday. And then we're going to reevaluate the procedure for each extension. So whenever you extend the fact with a new context, you're going to reevaluate the method based on that. It is going to be universally applicable. You can apply that to any kind of method you have in your program. But it suffers again that, what about recursion? How are we going to handle recursion in this case? The other approach, the functional approach, it does things in a way that is kind of similar to the monotone framework, but the monotone framework is specific to intra-procedural analysis, but here we're going to do it for inter-procedural analyses. And in that case, we want to compute a summary function per callee. So every method has a summary, and then we are going to apply that summary to every context that we have, every call site that we have. And depending on the context and depending on the information that the context provides, like the values of the arguments, the surrounding environment, we're going to compute something different. The good thing about the functional approach is that it can handle recursion just fine, because there is no, we can have an abstraction, we can abstract that function summary over recursion and over looping structures, as we're going to see. We're going to see also in our lecture on Thursday this week how this functional approach is kind of the first step towards implementing the IFDS framework, the Intraprocedural Finite Distributive Framework, subset problems. Problem with the functional approach is that it is not always applicable. There are certain cases where you cannot find a context-independent summary for the function that can be applied at different contexts. Sometimes it's just not possible to do that. The value of the summary is too dependent on the context that there's just no way around if reevaluating the method at every single context that you have. So let's discuss the first approach, the call strings approach. So how do you do that? How do we create this, these call strings? So here in our example we have a main method. The main method generates a secret, calls ID, then has a not so secret value, calls ID again, And the value, the function ID is just returning the parameter that is passed along. So it is basically an identity function. It doesn't do anything really interesting. And the goal here is that we want to make sure, we want to know like how we can differentiate between these call sites. So if we create the inter-procedural control flow graph for this program, we're going to have our main method here. This is going to be our main method on the left-hand side. This is going to be our ID method on the right-hand side. And the program is going to follow this. So first we have s equals secret. In the inter-procedural control flow graph, there's only one outgoing edge. We're going to go to ID. What is our fact? Our fact now, we are doing a taint analysis, so we are tracking what are the secret values in our program and how they affect, where they are going to be assigned to each other. So S is the secret value because it's assigned the value directly from calling secret. So S is now secret, so we have our data flow set, our data flow fact has the set S. Then S is is used as an argument to call ID, and then that value is assigned to ID. So we're going to go from this edge here, we're going to go to the control flow graph, or the starting node rather, in the ICFG of ID. We're going to pass S to P, because P is the argument of ID, so we're going to pass S to P. So P now is also secret. P is assigned R here, so in that case, the Vout, or the output fact of the statement, is that R is also secret. Then we are returning from R. There are two back edges that we can return from. One that goes to the first call to ID, one that goes to the second call of ID. So if we take R to the first edge here, then that's fine, but I can also take R to the second edge here, meaning that R is going to be reachable, meaning that R is going to be tainted. If I take the second one, that would basically mean that I'm returning to a call site that is not the call site that caused me to be here in the first place. S will still be tainted if it is going to be that call site here, and here V will be tainted if I follow this approach. So at that analysis, if the analysis follows this kind of data flow, it will say that both S and V are going to be tainted. But this is just wrong. And you can sort of tie that back to the way we talked about call stacks and the staircase of calls and returns, and how that helped us invalidate certain paths from our ICFG in our previous lecture. This is exactly the same problem here. And we're going to solve it in a very similar manner to how we solved the problem of invalid paths in the ICFG in our previous lecture. So how are we going to do that? So we're going to do that by associating every data flow fact with the call string. So what is a call string? So first here, this is S main. This is the first statement in main, or the starting point in main. I'm going to give labels to all the call edges, all the call sites. So I'm going to say this is C1, this is C2, and I'm going to start my propagation. So I'm going to start here, and instead of propagating facts, just S, I'm going to start propagating facts associated with how did I get here so far, the path that got me to that point. So here I got to that point through S main in my control flow graph. Now I have C1, so this is going to be my context. And whenever I'm propagating my fact, I'm going to push the context to whatever context I have so far. So here I'm going to have P as my data flow fact, because P is now the argument to ID. But I'm going to push this C1, and this is the value of pushing it to S main, to my call stack. So I'm going to have S main followed by C1. So think of this as a stack, and you're just pushing values on top of the stack as you go to maintain the context or the path that got you to that point. And now I have R equals P, so I'm going to have S main C1. The context didn't change because there's no further context to push, but now R is tainted, so R is going to be shown here as a data flow fact. And now when I'm returning, what would I do? Like, how would I know where to return to? Well, I'm going to look at my context and see, my context is S main followed by C1, and I'm returning. So I must return to that last element of my context, which is C1 here. This is where I'm going to know that I need to propagate back that value, S main C1, and R, that data flow fact, and I'm going to return that back to here to C1. So now when I'm pushing this forward, when I'm propagating the data flow fact forward, S is going to be tainted. I'm going to pop the latest value of my context once I returned. So it's going to be S main S again. Now after executing that statement, V equals not secret. So this is V is no longer going to hold a secret value. So again, only S main S is my data flow fact, which means S is still tainted, but V is not. And now when I have my ID, I'm going to propagate the value V to P. And in this case, I'm going to propagate things further. So still no problems there because V is not tainted anyway. So there is no need to propagate even that value further. Because remember from our previous lecture, you only propagate values that are relevant to your data flow analysis. You don't just propagate everything. If V is not tainted, there is no point in propagating that anyways, because it won't affect anything in the calling, in the callee function that you're calling. And when we return back again, it's going to be S main S as well, that is only tainted in our program. So having this call strings approach, we both did return to the correct point in our data flow, in our control flow graph, in our ICFG. And we also maintained the correct set of facts throughout the program, and we were able to always remember the path that led to the current statement so that we can differentiate or distinguish between these two method calls here, ID at C1 and ID at C2. And that not only allowed us to return to the correct point after finishing analyzing the analysis of a method, but it also allowed us to eliminate some unnecessary propagation of data flow facts that are just not valid to propagate at that point. So the general algorithm for call strings approach is call edges are going to be pushed. Call edges push the call site to the stack of the calling context of each propagated value. So you push C1 to the stack of those propagated values. Return edges only return to the method on the top of the stack, like we did with the first C1, the first call site to ID. And you need to find a way to handle merge points. So if you have two branches, for example, where you're calling methods in each one of them, you need to define your merge operator that can merge these two facts together, because now you're no longer propagating facts, but you're propagating facts that are associated with a call stack, or the call string rather. So it's a pair. The fact now is a pair, a data flow fact and a call string. So how do we merge facts here? So this operator means that you have a context X and a context Y, and you want to define a merge operator over them. This is going to be, formally speaking, this is going to be how we define them. So we are going to define our merge operator. Remember from our lattice theory lectures, this is going to be our merge operator. So assuming that you have a context, sigma, and you want to merge the data flow fact X and Y, this is going to be, or such that sigma X, basically sigma is the context where your data flow fact X belongs to X, and sigma is the same context that Y, the data flow fact, belongs to Y. This is going to be union sigma X, where sigma X belongs to Y, belongs to X, and for all Z, for all other values Z that are in L, those values do not exist in Y. You're going to make that union sigma Y such that that context sigma Y belongs to Y, but for all other values Z that are in L, sigma Z does not exist in X. So basically what we're saying is we're going to include sigma X in the output and sigma Y, and sigma X merge Y. And here we are going to include only sigma X such that sigma z does not exist in y, and sigma y such that sigma z does not exist in x. So this is how we're going to define our merge operator if we have two contexts that we want, or two data flow sets of data flow facts that we want to merge together. But that doesn't quite work actually in some cases. So what are the cases that this doesn't work for? So one big problem here would be context length. So when we looked at the call strings approach, we said that we're going to keep adding every context according to that algorithm. We're going to keep adding every context to the current context so far in the call string. So you have S main, you add C1 to it, maybe you have C3 afterwards, C4, C5, C6. So how long can your call string be? What if you have a recursive function? How are you going to handle that? So this is one problem there with the context. So now we are almost halfway through the class, so I'm going to stop here for a few minutes, and once we are back from the break, we're going to discuss this problem further, and we're going to see what are the solutions, or what is the solution that we're going to come up with to resolve or to address the problem of context length for the call strings approach. And then afterwards, we're going to, in the remaining time, we're going to talk about the function approach afterwards. So let's have a break for a couple of minutes, and we're going to reconvene again at maybe 1:17 or so Edmonton time, PM. Thanks, folks. All right, everyone. We are back again after the break. So before the break, we were talking about one of the major problems that face the call strings approach, which is how far can the call string grow to be? Because you keep adding contexts as you go, so you're basically equivalent to tracing back the call stack or whatever that may be that you're collecting the context from. But let's say it's going to be the call stack. So you need to handle a way, and remember that you're not doing this at runtime where you can literally just look at the call stack and see what are the method calls that you have so far, and that will be your calling context or your call string that you're tracking. But you're doing this statically, so you're not running your program, so you want to reason about that at compile time, statically speaking. So there must be a way that we can sort of work around this growing length of the context. And that solution is going to be k-limiting. So you're going to start hearing this term or this phrase many times from today's lecture and in our lecture on Thursday and also next week as well as you're going to see it a lot in the papers that we're going to read in the course, and maybe even in some of your course projects that you're going to do in the semester. So what is k-limiting? K-limiting is basically just putting a limit of some arbitrary chosen, in many cases, number called k, that is small enough that will allow you to just put a limit to how far or how big the call string can grow. You're just going to say that my call string can have at most 4 contexts in it, and that's it. The caveat of that is that if you choose k to be really small or smaller than what your largest context may be, you're going to be imprecise because you're not going to handle or distinguish between calling contexts that may have length that is larger than the length k that you chose to be small. On the other hand, if you lose a large k, if you say, well, yeah, maybe my largest context is now 5, so maybe just to be safe, I'm going to make my context length k be 7. Well, then you're not really making use of that solution after all, because you're choosing k to be really larger than you need, and that may lead to a poor performance by your analysis. Again, the same problem by having too large of a call string. That is going to degrade the performance of your analysis. And there has been a lot of research done in recent years to figure out whether we can actually, prior to our analysis or while the analysis is even running, to choose a proper value or a correct value or a good enough value for k, or maybe even just work around having the idea of having k-limiting altogether that limits our calling context in that regard. And we're going to have at least one paper in our paper seminars that address that, as we're going to see in the second half of the semester. But in all cases, even though that it is hard to choose a value of k that is adequate enough or useful enough, How does it really work? So let's say we found the magical value of k that we can choose. So how does it actually work now that we decided what k is? So this is call strings with k limiting. So we have k, method k, and in that case we're going to have our context c0, c1 up to ck. So basically this is your call string. And let's say that k you're going to call ca. So what are you going to do? Well, and in that ca, that context ca, you're going to call a. So what we're going to do? Well, here I'm going to drop basically that context c0, and I'm going to push ca again, because I can only have at most k call strings, right? So if you can have at most k call strings, and you need to always maintain the last call string or the last context to be able to return back to it after you're done, then you need to push this call string and push your new call string or your new context to the top of your call string. So you must always maintain a suffix of length k. That is really what k limiting actually means. You always need to maintain a suffix of length k. So k here would be the length of the, if you want to choose the correct value of k, it should be the length of the longest non-recursive call sequence that you may have in your program, so that you're able to distinguish between all these calling contexts that you may have in your program. So in this case here, in our case here, if L is your lattice that defines the domain of the analysis, then the cardinality of L, remember, the cardinality of L would be the lattice height, which would be the length of the longest chain in your lattice. Then the number of contexts that you need in your program to support the longest non-recursive call sequence would be k, which is the length of that non-recursive call sequence, multiplied by your lattice plus 1 squared, which basically means you can go up to your lattice all the way, like pretty much, and you need to return back from them. So you need to be able to distinguish between all those pairs of calls and returns. So you have the length of your lattice plus 1 squared. And at every single point as you go deeper in your lattice, you can have a k of non-recursive calling sequences. So that's why you multiply k by the cardinality of your lattice plus 1 squared. So that will give you the number of contexts that you have in your program. Now you need to differentiate between all of them. You need to either give a distinguished or a unique label to each one of them. So there was a paper by Ketkar and Karkari in CC, Compiler Construction, in 2008 that significantly improved this bound to the value k for k limiting to be k multiplied by the cardinality L plus 1 only. So it basically eliminated the exponent here and made it a bit more linear than polynomial in the previous worst case scenario. So to recap, we have two naive solutions, cloning versus inlining. Call strings approach is a more systematic approach here, where you use the context as your call string. You can merge call strings subject to constraints given how you define your merge operator, such that you can combine facts that are incoming from different contexts. Problem with call string is that the context length has to be bound by the value k, and there are different bounds, and researchers every other year or every year they come up with new approaches that try to push the boundaries of k limiting to either reducing the value, making the most out of a smaller value of k, or even working around the k limiting altogether by defining new abstractions and new approaches in program analysis that allow you to define context or distinguish between contexts without having the need to have k limiting, as we're going to see, like I said, in the second half of the semester with our paper seminars. So this is one approach for context sensitivity. Do you have any questions about call strings or context sensitivity so far before we move on to the functional approach? So there is a question here: will a DFA be helpful in solving the context length problem. This is the kind of solution that is similar to actually what we are going to discuss in one of the papers in the second half of the semester. So that paper, let me see. So this paper is, we haven't set the date for it yet, but it's the paper from PLDI 20, so this year, and it was one of the distinguished paper awards at the conference. It's fast graph simplification for interleaved dike reachability. And it's also closely related to some of the research that one of my students has done for his PhD for getting rid of k-limiting altogether by using push-down systems to represent the abstraction of the context and the field sensitivity and the flow sensitivity of your program abstraction as well. But yeah, we need to have some sort of abstraction that can abstract away the value, the actual context length. So that might be one way to go around it. Yes. No problem. Any other questions? All right. So now that we have discussed the call strings approach, the second approach, the counterpart of it, is the functional approach for context sensitivity, and it works in a very different way. So in the functional approach, I mean, if even like the first approach works pretty well, and seems to be other ways actually we can, like we have just discussed, that we can sort of work around the context length. Well, why bother with the functional approach in the first place? The answer will become more clear in our next lecture, but let me give you a quick overview of that. So let's say that we have a piece of code here. So here we're assigning my password to h.f, phone number to i.f, credit card number to j.f. And we have three call sites to foo, C1, C2, and C3. Foo receives two parameters, and it assigns a.f to c, c to b.g, and that's it. So it has some side effects. And then we have three method calls to print, and we're printing the value g of x, y, and z. So how does the functional approach work here? So the first call site foo, h.f, and then I'm going to pass it h and x. So what I'm going to do? Well, h is going to be assigned to a, x is going to be assigned to b, and then I'm going to propagate the data flow fact. So my a.f and c1, so remember, like every single data flow fact will be the data flow fact that you're propagating associated with the call string so far. So the call string here will be c1. Propagate that forward. Now b.g with c1 will be reachable, meaning it will be tainted in this case, and I'm going to return that. So I'm going to return here, then go to c2, go to foo again, now with different arguments, I and y. So propagate a.f c3 and propagate a.f c2 b.g c2 and then return. Then we have a third call site, c3. Propagate a.f c3, propagate forward, you calculate b.g c3 and return that again. So for the same method, just because you have more than one call site for it, we had to analyze it every single time in the regular approach. So that is kind of inefficient. Like, why would I need to analyze the same method more than once? Like, if the method can be summarized somehow, that can just, I'm basically recomputing the same data flow fact every single time I'm reanalyzing the method without any obvious gain here. So the functional approach does something that sort of resolves this kind of redundant computations here, or repeated computations here. So instead of analyzing the method 3 times using the regular approach, we're going to do something different here. So we're going to do that using the constant propagation as an example of our analysis. So here foo AB, increasing or incrementing A by 1, then I'm returning A plus B. Oops. So instead of analyzing the same method 3 times, the functional approach basically will create a summary of that method that we can then actually contextualize or parameterize with different values that we can get from the context at every single call site. And the idea would be, like I mentioned earlier in our lecture today, that you're going to analyze the method once, you're going to have a summary, which is a function that you can then apply to whatever arguments that you're passing along. And this functional approach is really fundamental in defining another formal framework for program analysis that we're going to discuss at length in our lecture next week, which is on Thursday, which is IFDS, or Inter-Procedural Finite Distributive Subset Problems, and how IFDS allows us, using that functional approach, where we're going to discuss at great length in our lecture on Thursday, how that functional approach allows us to have method summaries. You analyze the method once, you can then basically plug that summary into your data flow analysis and have a very systematic approach, a very systematic algorithm that is again configurable with various configuration parameters that we're going to see in our lecture next week, that would allow us to do inter-procedural analysis, inter-procedural data flow analysis, subject to certain constraints of the flow functions that you're defining, that will be scalable, will be precise, will handle context sensitivity, automatically handles flow sensitivity since it's using the inter-procedural control for graph, and it works in a kind of a similar fashion to the monotone framework that we discussed in our first couple of lectures in the course. That's actually all I had for you today. It's kind of a short lecture today, on Tuesday. On Thursday, we're going to discuss IFDS, and then next week, we're going to talk about, depending on how much we cover from IFDS on Thursday, we might still need some time on Tuesday next week to discuss IDE, to continue our discussion about IFDS, and then maybe move on to another more general framework called IDE, or the Inter-Procedural Finite Distributed Environment Problems. And then on Thursday next week, if we do have some time, we're going to talk about non-distributive analyses. Then the week after that, we're going to have our proposal presentations and our guest lecture, which I'm going to provide more details about over the next few days. After that, we're going to start with our paper seminars, the second half of the semester, all the way until we reach our final project presentations in the last week of lectures. That's all I have for you today. If you have any questions, please do ask me. We still have some time. If you don't have them now, please send me an email or ask me on the eClass forum, or ask IFAS as well. We'll be happy to help out and answer any questions you may have. Thank you all for today, and I look forward to seeing you on Thursday as well. Thanks. All right, so we do have one question here. How about the efficiency and precision of these two methods? What do you mean by these two methods? Do you mean the functional approach versus the call strings approach? Okay, so we are going to see actually more, I don't want to say formal, but more discussion that we're going to have about the functional approach when we talk about IFDS specifically next week, on Thursday. So we're going to have more a discussion about the exact complexity of the algorithm, and why that complexity can be relaxed in certain cases, and how we can improve that complexity even in certain cases, and what will be the worst case complexity of it. And generally speaking, we don't always, like, it's not always the case that there is only one winning algorithm. Again, it depends on the kind of analysis you want to do. In certain cases, calling context, like if you know, for example, because if you go back here, if you go back to the, was it this? No. Yeah. So if you go back here to k-limiting for the calling context, I mean, if your L is not that big and your K is not that big, then call strings approach is good enough. There is no point in going to the functional approach, right? Because you don't have a domain for your analysis that is that large that will cause your context to be that big. In practice, from my experience, I think calling contexts, I mean, you can go maybe up to 4, 5. More than that, it gets really bad really quickly, especially if you're talking about a recursive data structure like trees, hash sets, hash maps. These are the kind of collections or data structures that can tank any kind of context-sensitive analysis really quickly. You'll be surprised by how much this will affect the analysis. And in those kind of situations, the functional approach might be better off. But again, the functional approach has its own drawbacks, as we're going to see in IFDS. Keyword there is distributed. What does it mean for the flow functions to be distributive? We talked about that early on in the lectures. But what does that buy us? What does that? We also talked about that earlier in the lecture. But what's the implication of having all your functions to be distributive, and what kind of analyses you can solve and not solve having your functions distributive? So, long story short, both are good alternatives depending on the situation, depending on the analysis. And as a static analysis engineer or as a program analysis engineer, you need to figure out what is the best case for you. What is the best case for the problem at hand that you want to solve? Don't get hung up too much on I need to do this in a certain way, or I need to do it in like my way, or nothing, or for all or nothing kind of approach, because in practice you need to make some compromises there for your analysis to be scalable, for example, but still maintaining some decent level of precision that makes it useful, especially if you are going to report those results to developers. I hope that answers your question. No problem. You're welcome. Any other questions or comments or concerns? We all good? All right. Sounds good then. Well, thanks again, everyone. We're gonna talk again on Thursday. I look forward to our lecture on Thursday. Have a good couple of days until our next lecture, everyone. Bye for now.